we're going to go ahead and close out this section with a nice type of sum where things just collapse into each other. You'll see what I mean in a second. They're called telescoping series, and let's go on with it. So I have a sum here, okay? 1 over n times n plus 2, and I'm summing from n equals 1 to infinity. Now, that doesn't look like any of our special ones that we've seen before. That doesn't look like a geometric series, okay? And the terms probably look a little complicated. We just want to see if this series converges or not. I'm not worried about the partial sums yet. But if you see on the right, okay, right above me here, I did put this in MATLAB, okay, just so you can see like how these things behave. So I went ahead and wrote out the first 200, did the 250 partial sums, and I only printed out every 10. And you can kind of see that they're getting really close, but does it really get close? Round off error and stuff. Well, we're about to investigate that. Now, I want you to take a look at the summand here, okay? 1 over n times n plus 2. That looks oddly like something that we've encountered before. What do you think? Partial fractions. So the idea here is we're going to go ahead and do a partial fraction decomposition of this thing. So what I'm going to do is I'm going to go ahead and break this up into partial fractions, okay? So we have 1 over n times n plus 2. This is going to break up as something over n plus something over n plus 2. Okay, now if you need a refresher on partial fractions, please go ahead and watch those videos, okay? The recipe, the method, and all that. We're not worried about integrating here. We're just worrying about if this sum converges or not, and we can actually get this into a form that actually makes something nice happen. So if I go ahead and do the usual procedure, we'll have 1 equals a times n plus 2 plus b times n. And now if I use my cover-up method, my two clever values are going to be n equals 0 and n equals minus 2. Okay. When n equals 0, okay, I'll leave it to you to check that a is equal to 1 half. And when n is equal to minus 2, we'll get b equals minus 1 half. So how does this help us? Well, I can now write my sum, okay, as the following, okay? I can replace the summand as the following. So I'll write this. In fact, I'm going to go ahead and write this as from k equals 1 to n. I'm going to go ahead and do this so we look at partial sums first, and we can look at a limit here, okay? So I'm going to have, well, let's see, we have 1 half over n, and then I have a minus 1 half over n plus 2, okay? Just replacing, because we now know that this thing here can be written as this thing here with a and b replaced as the appropriate things. Now I'm going to do something nice. I'm going to go ahead and pull the 1 half out. Okay, I'm going to go ahead and factor out a 1 half here. We have 1 half times this sum from, and let me make sure that my indices are correct here. K equals 1 to n of 1 over k minus 1 over k plus 2. Now I'm going to go ahead and write out some terms of this thing. We're going to expand and explore, okay? Let's see what happens here, okay? So when I do this work, I'll have 1 half times, well, we're going to go ahead and think about this, right? When k equals 1, my pairing is 1 over 1 minus 1 over 3. Then when k equals 2, I'll have 1 over 2 minus 1 over 4. And then next we'll have k equals 3, 1 over 3 minus 1 over 5. And just for good measure, okay, 1 over 4 minus 1 over 6. And you'll see that this pattern will continue, right? And this will continue all the way up to when k is equal to n. But I'm actually going to go ahead and do this, write this, so that we're going to look at the last three terms in this series, okay, in this truncated series, okay? So I want you to note here, this is what happens when k equals 1, when k equals 2, when k equals 3, when k equals 4. Now I want you all to see what happens when I have k equals n minus 2. Okay, when k equals n minus 2, okay, I'll have 1 over n minus 2, then minus 1 over n minus 2 plus 2. Well, what's n minus 2 plus 2? That's just n. So I have 1 over n there. Then, when k is equal to n minus 1, okay, 1 over n minus 1 and then minus 1 over n minus 1 plus 2. That's n plus 1. And then our last term here is when k is equal to n, we'll get 1 over n minus 1 over n plus 2. Okay? So let's make a note there. That's when k is equal to n. That's when k is equal to n. Okay. So it may not look like I've done much, but I want you to take a look at what happens here, okay? The terms I'm going to highlight in red are ones that will not survive. What does that mean? We'll take a look here. I have a minus 1/3, and I have a plus 1/3 here, okay? If I drop the parentheses, okay, addition is associative. So those terms add to 0. Okay, let's do a different color here. Let's see. I have a minus 1/4 and a plus 1/4. Well, those terms also die out. And then in this grayish color, minus 1 over 5. And then what will come up here is a plus 1 over 5 somewhere in there for k equals 5. So that dies off. And likewise, minus 1 over 6, let's do this in green. Minus 1 over 6 will kill off somewhere here. Everything except for these two that I'll circle in this dark green here, this 1 over 1 and 1/2, these survive. Okay, these two terms survive. Okay, but everything else, take a look if we keep going down the line, right? Okay, this 1 over n will cancel this minus 1 over n. Okay, we're kind of running out of colors here. This 1 over n minus 2 will cancel with something here with a minus. Okay, and then I'll have a n minus 1. Let's see, this is my last color here. This 1 over n minus 1 will cancel with something here. And so the two terms that survive in the tail, okay, two terms that survive in the tail are these two. So when everything collapses, this is an example of what's called a telescoping series, okay? This is an example of a telescoping series, okay? This is an example of a sum that telescopes, okay? When the dust settles, okay, what do we have left? Well, we have 1/2 times 1 plus a half minus 1 over n plus 1 minus 1 over n plus 2. Notice that I have two terms in the head that survive and two terms in the tail that survive. Okay, and notice that my denominators here have a gap of 2. Okay, now this here that we just computed was just the partial sum. This is just the nth partial sum. And remember that the infinite series converges if the sequence of partial sums converges. So now we just need to take a limit, and if you remember something from Calculus 1, I have something of type 1 over n. Well, as n goes to infinity, okay, as n goes to infinity, this is where the magic happens. Those two terms in the tail, okay, as n goes to infinity, these things go to 0. Okay, they decrease down to 0. And so my limit here is 1/2 times 1 plus a half, which if you do the work here is 3 over 4, which agrees with the MATLAB results up there. Okay, so this sum indeed converges. Okay, so what happened here? We had to expand our summand here and then do some exploration, see which terms survive and see which terms die, okay? And then once the dust settles, we get a thing for our partial sums, we can go ahead and take a limit. Okay, let's take a look at this last one here. We're summing log of n over n plus 1. Okay, now of course I could probably do partial fractions here or whatever. I could do the long division, but I don't have to. Okay, see, this one collapses in a nicer way here. Okay, remember those log properties, okay? If I have the logarithm of u times v, any logarithm base, or rather, this one I want to do, log of u over v, log of a quotient, that's the log of u minus the log of v. Logs turn quotients into differences. Logs turn division into subtraction. So we're going to go ahead and use that log property here. Okay. You write this as a sum from n equals 1 to infinity of, okay, let's write it like this. Log of n minus log of n plus 1. Now, let's just do some exploration and see what happens, okay? So every time we have an n, okay, we're going to take the log of n minus the log of the next thing, okay, and that's our pairing. So what do we have here? Well, we have log of 1 minus log of 1 plus 1. Well, that's 2. Log of 1 minus log of 2 plus log of 2 minus log of 3 plus log of 3 minus log of 4. Now you probably see what's happening here, right? I'm not even going to bother to truncate this, okay? But take a look at what happens here, okay? We'll have log of n plus, or rather minus, log, of n plus 1. And now what's going to happen? Well, take a look here. I have a minus log 2 here and a plus log 2. Those drop. Minus log 3 and a plus log 3. Those drop. Minus log 4 and a plus log 4 here will drop. And then soon I'll have that log n drop out. Okay, well, there's something fishy going on here, okay? Let's take a look at the partial sums, okay? So if I look at the partial sums here, Sn, so this is going to be the sum from k equals 1 to n of log of k minus log of k plus 1. Okay, if you notice that if I truncated this, okay, if I stopped there, right above where my finger is, if I stopped at n equals n, well, in this case, k equals n, the only thing that survives is minus log of n plus 1. Well, okay. You can see that, right? If you just experiment, right? If you just write out the first 2 partial sums, you'll see that pattern. But does that go to 0? The answer is no, okay? The answer is no, okay? We have to note the following, that the limit as n goes to infinity of minus log of n plus 1 is not 0. Further, it's not even a number. Well, rather, it's not even a finite number. Okay, let's take a look at what the graph of log of minus log n looks like, okay? So if I look at the graph of minus log n, okay, because it's the same if it's minus log n or minus log of n plus 1, okay? Well, the minus sign will flip it up, okay? That's a reflection about the x-axis, okay? And if I think about this, okay, just go back to my parent functions here. This is the graph of log of n plus 1, but with a negative sign. And if you really think about it, if you graph this in Desmos, this goes to minus infinity. So what's the problem here? This is a divergent sequence. And because this is a divergent sequence, okay, this sum diverges. And that's it. The sequence of partial sums is divergent, so the series itself is divergent, okay? So these were some special examples of the so-called telescoping sums. One where things actually collapse into a nice form and we got a number out of it. The other, well, things still collapsed, but we got a term that was just growing and growing infinitely. Okay? So telescoping sums, why are they called that? Well, because, take like one of those old collapsible telescopes and just collapse it into itself. All right. Well, that's your introduction to series there. Okay, we now know how to compute certain sums. We know how to do this exploration. We know how to think about partial sums, convergence and divergence of series. But as we move on for the rest of this chapter, sometimes we're not even concerned about the actual value of these sums, but rather, do they even converge? And sometimes we won't even need to figure out what the actual number is. Some we may estimate, some we can take a guess at what the result is. I wonder what you think what we're going to do, huh? We're going to develop a lot of things from our toolbox here. I'll see you in the next one.